Tungsten has the highest melting point of any pure metal, more than 3,400 degrees Celsius. But inside a tokamak fusion device, the plasma core can reach temperatures above 100 million degrees Celsius. This core plasma must never directly touch the machine wall. Magnetic fields suspended inside the vacuum vessel, but collisions and turbulence still transport plasma heat, helium, and charged particles across the last closed magnetic surface. This exhaust is guided toward metal surfaces at the bottom of the tokamak. In ITER, their steady-state heat flux can reach about 10 megawatts per square meter, with higher levels during some transients. The component that must receive this exhaust is called the divertor. But even tungsten cannot survive for long if all that energy is concentrated onto a narrow strip of its surface. So how can a divertor remove heat, helium-ash, and escaping particles from a tokamak without destroying itself? The answer is not an indestructible metal. Engineers must control the plasma's path, disperse its energy before impact, and carry the remaining heat away. A tokamak has a donut-shaped vacuum vessel. Its plasma cannot maintain that shape on its own. Magnetic coils create field lines around which charged plasma particles spiral. Shaping those lines keeps the hottest plasma away from material surfaces. At the plasma edge is a boundary called the separatrix. Inside it, closed magnetic surfaces keep particles circulating around the tokamak. Outside it is the scrape-off layer, where field lines are open and eventually intersect a material surface. This becomes an escape corridor for heat and particles leaking from the core. Near the bottom of many tokamaks, these field lines pass through an X-shaped magnetic structure known as the X-point. From there, they split into branches that extend down toward the divertor. The divertor is not simply a metal plate. It is the endpoint of a magnetically shaped exhaust system. ITER divides its divertor into 54 large cassettes. Each contains a support structure, a dome, and targets positioned where the field lines deliver the exhaust. Behind the armor are heat-conducting structures and water channels. Passages below lead to vacuum pumps that remove helium, unreacted fuel, and impurities. But this structure only explains where the exhaust goes. It does not yet explain why the targets do not melt. The danger is not only the total escaping heat. It is the area through which that heat must pass. Particles follow the field lines toward the targets, concentrating much of their energy in narrow bands called strike points. This is where the kinetic energy of the particles is converted into heat inside the material. If this footprint is too narrow, the surface heats faster than the cooling system can respond. Tungsten can crack, erode, or melt locally. Ions from the plasma can also strike the surface and knock tungsten atoms free. This process is called sputtering. Even traces of tungsten in the core can cause trouble. Its high atomic number makes it an efficient radiator, useful in the exhaust region, but capable of draining heat and reducing fusion performance in the core. The divertor must perform opposing tasks. It must remove heat and impurities without contaminating the core with its own material. It must cool the exhaust before it destroys the targets without cooling the core plasma. It must maintain this balance as plasma power and conditions change. Thicker tungsten or a stronger water pump cannot solve this if the energy remains concentrated over too small an area. So how can engineers reduce the heat flux before it reaches the metal surface? The first protective layer is not tungsten. It is the shape of the magnetic field. Adjusting the X-point and divertor leg geometry changes where the exhaust reaches the targets. Field lines approach at a shallow angle, lengthening the footprint and spreading energy across a larger area. Advanced configurations may extend the exhaust path or spread the field lines farther apart, but geometry alone has limits. For a larger reduction, the plasma exhaust must lose much of its energy before reaching the target. Operators introduce precisely controlled impurity atoms into the plasma edge. Collisions transfer energy to these atoms, which release it as electromagnetic radiation. Instead of striking one narrow band, a significant fraction of the energy becomes radiation distributed across a broader region. As divertor density rises and temperature falls, more frequent collisions, charge exchange, recombination, and radiation continue removing energy. If conditions are controlled correctly, volumetric processes reduce the plasma pressure, ion flux, and heat flux at the target, while the main radiation and ionization region moves away from its surface. This operating regime is called plasma detachment. Detachment does not mean the plasma escaped its magnetic field or fusion stop. It means the energy and particle flux have been greatly reduced before reaching the surface. The exhaust passes through a relatively cool, dense, strongly radiating region in front of the divertor, instead of striking with all its original energy. But the operating window is narrow. Too little cooling leaves the target endangered. Too many impurities or a cold region moving toward the core can reduce fusion performance and destabilize the plasma. Detachment is therefore a dynamic state, not a simple switch, and requires continuous control. Only after magnetic geometry and radiation disperse much of the energy does the armor receive what remains. Tungsten offers a high melting point, low vapor pressure, and strong erosion resistance, but it does not work alone. In ITER-style targets, small tungsten blocks form the armor. Beneath them, conductive copper alloy surrounds water cooling tubes. Heat crosses the tungsten and copper into flowing water, which transports it out of the vacuum vessel. Tungsten faces the plasma, copper conducts heat rapidly, and water carries it away. We can now follow the complete journey of the exhaust. Deuterium-tritium fusion produces an energetic helium nucleus and a neutron. The electrically neutral neutron does not follow divertor field lines, and is not part of the exhaust path described here. After the charged helium nucleus transfers much of its energy to the plasma, it becomes helium-ash and must be removed to avoid diluting the fuel. Heat, helium, and particles cross the last closed magnetic surface, enter the scrape-off layer, and follow open field lines. The X-point divides the exhaust into branches leading toward the divertor. Field geometry spreads the footprint. Controlled impurities convert heat into radiation. Collisions cool the exhaust and can produce detachment. The remaining energy reaches the tungsten armor, passes through the copper structure, and enters the water cooling circuit. All particles that lose their charge become neutral gas. Vacuum pumps remove helium-ash, unreacted fuel, and impurities. Diagnostics monitor temperature, density, radiation, strike point position, and plasma state. A control loop adjusts magnetic fields, fuel delivery, and impurity injection. If a strike point moves, the heat load on the target changes. If the detached region advances too far, it can affect the plasma core. If it retreats too close to the surface, the target can overheat. The divertor is not passive. It is where plasma physics, electromagnetism, materials science, heat transfer, vacuum engineering, and real-time control meet. Even then, thermal cycling, erosion, and neutron radiation age the targets, so divertor cassettes require remote removal and replacement. A divertor does not survive by confronting plasma at hundreds of millions of degrees with a sheet of tungsten. It survives by controlling the entire journey of the exhaust. Magnetic fields guide plasma heat and charged particle exhaust away from the core. Divertor geometry spreads that exhaust. Radiation and plasma detachment reduce its energy before particles reach the material. Tungsten receives the remaining heat load. Copper structures and cooling water carry the heat away. The vacuum system removes helium-ash and impurities from the machine. No single component can solve this problem on its own. And that is why the divertor remains one of the hardest challenges on the path from a fusion physics experiment to a power plant capable of continuous operation. To keep an artificial star alive inside a machine, engineers must do more than create an extremely hot plasma. They must also build an exhaust system sophisticated enough to handle everything that plasma leaves behind.